Alice. I'm so glad to meet you on iCANX this special event named iCANX Summit. Actually, I planned this great event, for a long, long time. We hope to invite all the people, the important, speakers get on iCANX, go together. So this event was a start, yesterday we have some interesting talks, from students. And today was a full day, very long program. So I'm Alice Zhang, also from Beijing. Warm welcome all of you to join on this. And first, let me introduce a little bit about program for today. Today was the first day of this iCANX Summit. We have a day program is for the special sessions. We have 8 special sessions in the morning 4, in the evening 4. So all these sessions was talk about a specific, topic. So in the evening, we have a big celebrations is for a plenary session. So today was our first plenary session. We invited 2 very important people, VIP. First is Professor Jagadish. He's our great friend, and he served as iCANX moderator and co-organizers in the last 2 years. And this year he has some new position, very important position. Then he's going to give a talk here. So we have another speaker is from Professor Hong Ping. He's from Beijing Sport University. He's very interesting. He's in charge of the technical program in Winter Olympic Beijing. So that's why I wear this, to celebrate for the Winter Olympic. Today he's going to tell us some high-tech used in the Winter Olympic Games, and he'll talk all the secret there. So today these 2 talks will give us a lot of, new information, new technologies. So without further ado, first let me introduce, get my colleague Fu Lan here to, charge for our Professor Jagadish talk. Lan, your time, please.
Thank you very much, Alice. Hi, everyone. Welcome to the iCANX plenary sessions. It's with immense pleasure I'm introducing you today the first plenary speaker, my long-term collaborator and great mentor, Professor Jagadish. First, let me just read out his fully condensed bio, because I know Jagadish has a very, very long list of great honors, but I'm going to just highlight a few. Professor Chennupati Jagadish is a distinguished professor and head of Semiconductor, Optoelectronics and the Nanotechnology Group in the Research School of Physics, Australian National University. Professor Jagadish is the editor-in-chief of Applied Physics Review, which is a very high impact factor journal, which has an impact factor of 19.16. And he's the editor of 2 book series and serves on editorial boards of 19 journals. Professor Jagadish has published more than 1,000 research papers, holds 6 US patents, and co-authored many books and co-authored many, many books. He's also a fellow of 11 science and engineering academies in US, Australia, Europe, and India, as well as 14 professional societies. Professor Jagadish also received many, many very highly prestigious awards. Just to name a few, which is such as IEEE Pioneer Awards in Nanotechnology, IEEE Photonic Society Engineering Achievement Award, OSA Nick Honyak Award, and ARMI's Somia Award, UNESCO Medal for his contribution to development of nanoscience and the nanotechnology, and Lai Medal from Australian Academy of Science. He also received Australia's highest civilian order, AC, the Companion of the Order of Australia, for his contribution to physics and engineering, in particular nanotechnology. Professor Jagadish has been elected as the next president of the Australian Academy of Science, and he's the first Australian of Asian heritage in this role. So without further ado, let's welcome Professor Jagadish to the stage to deliver his plenary talk on semiconductor nanostructures for optoelectronics applications. Please, Professor Jagadish.
Okay, Thank you very much, Pulan, and thank you very much, Alice, for that kind introduction, and also inviting me to participate in this important iCANX Summit. It's a really pleasure and honor for me to participate in this one. So today, as we mentioned, that I'm going to talk about semiconductor nanostructures for optoelectronics applications, in addition to being a professor at the Australian National University. And I also have honorary appointments in various parts of the world, and it's a pleasure and honor for me to be associated with many of my colleagues, including many in China as well. So this is really a collaborative effort between my group at the Australian National University and many groups in Australia, US, UK, China, Sweden, Italy, Russia, Switzerland. The beauty of science is that there are no national boundaries. We can all work together. And then I really enjoyed working with my colleagues in various parts of the world. And also many students and postdoctoral fellows have contributed to our joint research. I want to thank all of them and for enriching and enabling us to be able to do exciting science. This is my group at the Australian National University, and we typically 10 to 12 nationalities at any one time, and bright young people. It's a really pleasure for me to work with all of them, and I want to thank them for their contributions to our research, and both the present members as well as the past members of the group as well. Within the group, there are many academic leaders, and in fact, Professor Ho Tan, Professor Lan Fu, who is chairing the session, is leading some aspects of our research, and Dr. Shiva Karaturi and Dr. Zion Lee, and also many of my colleagues, those are now working in other parts of the world, and then I also want to acknowledge them for their leadership to the various research activities, which I will keep mentioning when I'm talking about this particular various aspects of our research. And I also want to take this opportunity to thank our funding agencies for their support, allowing us to be able to have fun. So here is an overview of my talk, and I'm going to really talk about the motivation, why we're interested in semiconductor nanostructures, and I'm going to talk about growth of nanowires and nanostructures, and then talk about a wide variety of devices made out of these nanostructures, and I'll draw some conclusions. And before proceeding further, I would like to thank many groups, those who are working in various parts of the world in the field of nanostructures and nanowires, and then for enriching our discipline, because it's important in science to acknowledge other groups, those who are working in our disciplines. Before proceeding about nanostructures and nanotechnology, let me really talk about industrial revolutions. And as most of you know, that the first technological revolution started with steam power, led to mechanization. Second industrial revolution started with electrical power, led to mass production. Third industrial revolution started with computer power, led to automation. And people are predicting in the fourth industrial revolution, and the biological world and digital world will come together, and will be really interfacing the humans and machines, for example, using light-based technologies, because of the fact that about 80% of the information which we receive is through light, for example. And currently, the light-based technologies are about 1 trillion Australian dollars, and people are predicting by 2030, these technologies will be doubling, and that means there's a large amount of opportunity for all of us to be able to make contributions to this particular area. So the World Economic Forum has identified the holographic displays, and which are coming out of your phones, for example, and wearable optical sensors monitoring our health, and light navigation and communication, LiDAR for autonomous vehicles, and then also the 3D vision and gesture recognition, and enhanced machine vision and augmented reality. And all these technologies require smart miniaturized optical systems. And then now, as part of the ARC Center of Excellence, Australian Research Council Center of Excellence, TMOS, and we are really using nanostructures to develop light sources like lasers and LEDs and single photon sources, and then manipulating light using meta-optics, and then using nanostructures to be able to detect light as well. So really, you need to generate an optical system, all three types of these three aspects of it. And this particular center has been led by my colleague, Professor Vladimir Neshev, and 5 different universities are participating in this particular center. Optoelectronics. What is optoelectronics? And all of us know about electronics, and whenever you're using computers and then any electronic devices, most likely they're made out of silicon. You're manipulating electrons. In the case of optoelectronics, we are converting electricity into light for LEDs and lasers, and otherwise are converting light into electricity in the photodetectors and solar cells, for example. But as it turns out that the silicon is a workhorse for the microelectronics industry or nanoelectronics industry, but unfortunately, it is not a very good light emitter. If you want to make LEDs and lasers, you need to have direct bandgap semiconductors. That's where we end up making use of group 3,5 semiconductors of gallium arsenide, indium phosphide, gallium nitride, gallium antimonide, combinations of these materials. These materials have got different band gaps, the energy difference between the conduction band and the valence band. So by essentially mixing various materials, we'll be able to generate different colors of light. Just to give you one example of development of the gallium nitride technology has led to the development of the blue LED, which led to Nobel Prize for these Japanese scientists in 2014 in physics, because of the fact that till that point, there was no blue LEDs or highly efficient blue LEDs were not available. So now, since you got all three primary colors, you can really make the white LEDs. And nowadays, of course, you're talking about solid state lighting, large area displays, and LED lighting is also playing an important role. In fact, some of my students are manufacturing millions of LEDs a month in China, for example. And the same materials which are used for making LEDs could also be used to make lasers, for example, for displays to machining, to cutting and drilling, and as well as also laser surgery to communications as well. And in fact, today I'm able to talk to you because of internet. Internet really relies on optical fiber communications, where we make use of lasers and photodetectors. So these materials which are used for making light emitters also can also be used for detectors. And in this case, we can make use of them for biomedical imaging applications, infrared detectors, night vision applications, and also solar cells, which are made out of these multi-junction solar cells by stacking different semiconductors of multiple junctions, and we'll be able to achieve the efficiencies as high as 47%, for example. Okay. So the challenge is that these are all developed for the space applications, but now people are looking at how we can make use of them for terrestrial applications, like concentrator systems, for example. Challenge is to reduce the cost, and that's what we and many other groups are working on, how we can make use of nanostructures to be able to reduce the cost while improving the efficiency of these structures. So nanowires are seen as building blocks for the next generation electronics and photonics. And one of the unique things with the nanowires is that the lattice mismatches are no longer an issue. You can make nanowires of any material on any substrate because of the nanoscale interface between the substrate and the semiconductor. Then what happens is that this can relax without creating any dislocations in principle. So lattice constant is a unit cell which repeats itself in a crystal. You can also make radial heterostructures. These green materials and red materials are different, and that means you can be able to put quantum disks and things like that, for example. You can also make PN junctions, and also you can make within the nanowires so that you can make lasers and LEDs or so, which I will come back to. You can also make radial heterostructures or core shell nanowires and the branch nanowires as well. So in fact, there are reports from our own group where we have demonstrated gallium antimonide nanowires can be grown on top of gallium arsenide despite large lattice mismatch. You're shown you can get atomically perfect gallium antimonide, which is very good for infrared detectors. You can also make branch nanowires of indium arsenide on top of gallium arsenide, which are very good for the cantilevers and scanning probes or so. We've also demonstrated indium phosphide nanotrees, which are good for energy harvesting applications like splitting of water to generate hydrogen. And then also we are moving from nanowires to nanomembranes and other exotic structures, which I will come back to. Already there are many reports in the literature about various photonic devices which have been demonstrated, and then I will share some of our own results. But also most recently, IBM Zurich has demonstrated indium gallium arsenide nanowire transistors on 6-inch wafers of silicon, indicating that the nanowires are going to play an important role in electronics as well. If the nanowires are of so much of importance, how do you make them? There are two main techniques we make use of, and mainly we use metal organic chemical vapor deposition, or MOCVD. This is an industry standard technique, which is a scalable process. You can also use molecular beam epitaxy, and then we end up choosing MOCVD. In this case, we use metal catalyzed Vrs growth process. In this case, we use gold nanoparticles of different diameters, and it turns out that the gold has got a melting temperature more than 1000 degrees Celsius. But once if it reacts with gallium or aluminum or indium, its melting temperature reduces to 350 degrees Celsius. So now, if you put these gold nanoparticles on top of a gallium arsenide substrate or any semiconductor substrate, and then put this one into the MOCVD reactor and heat it up to somewhere between 370 to 500 degrees Celsius, And then you end up creating this gold gallium eutectic liquid. And then you introduce the gases needed for the growth of gallium arsenide, trimethyl gallium and arsine. These gases get incorporated into this liquid alloy. It gets supersaturated. Crystals start precipitating out. So because you're introducing a vapor into a liquid and getting a solid, Wagner and Ellis and Bell Labs in 60s, they've called this the technique called Vrs Growth Process. And my former student, Dr. Hannah Joyce, during her PhD, she has demonstrated these excellent quality gallium arsenide nanowires with no tapering, no twin defects, and also you can control the dimensions of these diameter of the nanowire essentially by changing the diameter of the nanoparticle which you're using. And this is about 15 years back or so, we demonstrated these ones, and these atomically perfect nanowires are important for optoelectronic devices, for example. And we made the nanowires as small as 10 nanometers, as big as 300 nanometers. We choose different diameter nanowires depending on what applications you have. The alternative technique is called selective epitaxy. In this case, we don't use any metal nanoparticles because sometimes you don't want to use metal nanoparticles. It's not compatible with the process. For example, you don't want to put gold nanoparticles on top of silicon because it acts like a non-readily combination center, for example. So we deposit some silicon dioxide, spin coat some ZEP photoresist, and do electron beam lithography of holes, and then transfer those holes through wet etching process, for example. Then we put this one in the MOCVD reactor, heat it up to somewhere between 60 to 750 degrees Celsius, introduce the gases needed for the growth of indium phosphide, in this example, trimethyl indium and phosphine. You can see you get a uniform, nice nanowires, and also you can see beautiful hexagonal facets. And this work is my student, former student, Dr. Chiang Gao, and who worked also very closely with Professor Lan Hu and Professor Ho Tam, and where she has demonstrated excellent quality gallium arsenide, indium phosphide nanowires. Now we take these nanowires and excite with the laser pulse and measure the light emission from these ones, so-called photoluminescence. And then we really compare the performance of these nanowires and with respect to the epitaxial layers grown this blue curve. And then you can see that the both nanowires and epitaxial layers are showing very similar quantum efficiencies, indicating that the surface non-rate recombination is not a major problem in the case of indium phosphide, and we can get excellent quality performance from these ones. That is not always the case. For example, in the case of gallium arsenide, surface non-rate recombination velocity is very, very high, and you need to really coat this one with the passivation of the surface by coating with aluminum gallium arsenide or so. Otherwise, bare gallium arsenide nanowires are difficult to really make them to emit light efficiently, for example. So then we asked ourselves, instead of opening holes, what will happen if you open a slots or rings? This is the work of Dr. Nain Wong, and who is now a postdoc in the group. And during his PhD, again, he's taken indium phosphide substrates, deposited some silicon dioxide, put some PMMA or ZEP photoresist, did electron beam lithography, and transfer those patterns through etching. And again, he spent a lot of time in optimizing various growth conditions. And again, every student spends huge amounts of time in optimizing and be able to get good quality results. And I want to thank my students and postdocs, those who really passionately put a lot of effort in order to be able to get these beautiful results. So here's the case when I won't really open this slot along this particular crystallographic orientation, puts into an MOCVD reactor, heat it up to somewhere around 680 degrees Celsius, introduce the gas needed for the growth of indium phosphide. You can see you get the beautiful indium phosphide membranes, and then with these sidewall facets of this particular orientation here, for example. But if you open this slot along another crystallographic orientation, which is shown here, and if you do the same thing, and you also get the membranes, but in this case, you end up getting a different light facets. For example, also these membranes are a bit thicker than these ones because of the lateral growth is taking place. But if you open the slot in between these two orientations, and in that case, you end up having these beautiful these diamond-like structures with these alternating facets or so. And you can see that now, instead of just making nanowires, we can make all sorts of exotic structures. What will happen if you open a ring? Again, you can see that if you open a ring and grow these under, again, optimum conditions, again, you can see that Nain Wong has changed lots of growth parameters, which I will not have time to go to the details. You can get these beautiful ring-like structures. If you keep on growing further, you fill this gap here, you end up getting a nanomembrane. If you keep on growing further, you end up having these hexagonally faceted structures, for example. Again, these are very useful for nanomembranes and for MEMS applications and nanomembrane lasers and wide variety of sensors and other things as well. So we've taken these nanomembranes, nanodiamonds, and nanorings, and we did something called cathode luminescence. In this case, we put this one into an electron microscope, excite these nanostructures with an electron beam, and look at the light emission from these structures. You can see all these nanostructures are emitting very bright light and very uniform light, indicating that the 9 Wong's hard work has really paid off. These are very good for making optoelectronic devices, which I will come back and then share with you how we are making use of these ring resonators for making ring resonator lasers. So now we can see that we've asked ourselves, what else can we grow? So now we can see that the sky is the limit. You can make whatever the structures you want to have. And we're making ring-like structures, and then star-like structures, and antenna-like structures, and spirals, and gear-like structures, and all sorts of ones. Really looking at the impact of the shape of the nanostructures on the electronic and optoelectronic properties. So till now, I've really spoken about materials and the growth process. So now let me move towards devices. All of us have studied about lasers, and then we've been told that you need to have a gain medium. You need to have laser cavity by putting some mirrors, and you need to pump the gain medium. And then you really, once you pay the population inversion, as and when the model gain is equal to the optical losses in this cavity, lasing starts taking place. This is an undergraduate optics courses we all have studied. In fact, this equation here says exactly the same as this particular schematic here, for example. So now if we take a nanowire, and if you shine light on top of that one, then what happens is the light start propagating along the length of the nanowire, because nanowire acts like a waveguide, like an optical fiber, for example, because of the high refractive index of 3.4 in the nanowire of gallium arsenide or indium phosphide, and with respect to the surrounding medium of refractive index of 1, for example. But because these are also made out of 3-5 semiconductors, which are direct bandgap semiconductors, most of them, and then they also got a gain. And both ends of the nanowire acts like mirrors because of the refractive index difference between the nanowire and the surrounding medium. So now we can see, if I design my nanowires correctly, and each nanowire should act like a laser cavity, and then it should act like a laser, for example. We've been working in this area for a long time. And again, my colleagues, those who have contributed to this work have been listed here. And so particularly, Professor Sudha Makapati has been working particularly with colleagues like Dr. Vrs Saxena and Dr. Tim Burgess, and Professor Lang Fu has been working with Dr. Chiang Gao, and Professor Ho Tan has been working, all of them, in terms of the growth process also. But I'll not have time to go into the details of all these lasers. I'll give you one or two examples. So Dr. Vrs Saxena, who is now at Imperial College, who did during his PhD, has designed these nanowire lasers and looked at the light propagation of various optical modes. Here is an example of a TM01 mode, which is like this one, through a 260 nanometer gallium arsenide nanowire, for example. So based on the simulations of Vrs Saxena, Dr. Jenny Jiang, who is at Cambridge University, she has grown these structures of these nanowires of gallium arsenide, aluminum gallium arsenide, which are about 6 microns long or so. So now we can see that we transfer these nanowires onto a glass slide and excite with the laser pulse and look at the light emission. You can see a very broad light emission below threshold, a spontaneous light emission, and above threshold, you end up getting stimulated light emission and a narrow line width or so. And you see beautiful interference fringes coming above threshold. And in fact, they're very much comparable to theoretically simulated ones. And again, light output versus pump intensity showing threshold-like behavior, log-log plot showing the S-type behavior, confirming that they are all lasing. These are the first gallium arsenide nanowire lasers operating at room temperature. We demonstrated about a decade back or so. So what are we doing with these lasers? And then, by the way, these lasers are really 6 microns long. So it means we can put about 10 to 20 lasers within the width of your hair. That really tells you how tiny these lasers are. So we are working with my colleagues at University of Strathclyde, Professor Martin Dawson's group, where they developed a nanoscale transfer printing technique. They come up with a PDMS stamp, and they can pick up these nanowires, and then they really drop them wherever you want it to be. And again, this took quite some time. And in fact, the research fellow in their group, Dr. Ben-Hagul Hebert, has spent a lot of time in developing this technique. So here's the case where we transfer these nanowires onto flexible glass substrates for flexible optoelectronics applications. And you can see these nanowires in the optical image, and you can see the nanowires lasing, and you can see that nice threshold-like behavior, narrow line width, indicating that this transfer process is a gentle process, and we have not created any damage during this transfer process, for example, which is very important for applications. And also we've another student, Dr. Dimitar Jevtiks, and who has also really placed these ones in front of these polymer waveguides of SU8, which are very good for multiplexing and demultiplexing applications and polymer optoelectronics applications. We place these nanowire lasers here and excite them and look at the light coming out of this particular Y junction. You can see you get the very bright light emission here, indicating that these are very good for multiplexing and demultiplexing applications in polymer optoelectronics as well. So then we asked them, can you be able to locate these nanowires, nano antennas, for example? And this is the work of my young colleague, Professor Fang Ren, who is now a full professor at Nanjing University, while she was working at ANU, and then she's been making these so-called terahertz metamaterials, and she was creating these nano antennas. So then you can see that my colleagues in the staff slide are able to locate these nanowires very nicely. You can see the close-up of this one here. The nanowire is here, the nano antenna is here. If you do not have any nano antenna, as I've shown you, if you pump these nanowires, light is coming from the both ends of the nanowire, as shown here, and then essentially because nanowire acts like a fabricator cavity. But whereas you've got the nano antenna, suddenly light is coming from the vertical direction in view of the fact that now this nano antenna is changing the radiation patterns, for example. You can see the light output versus a pump fluence, and you can see the threshold-like behavior, narrow line width, indicating that these are the first vertically emitting nanowire lasers. Now we can use them for facial recognition applications by putting two-dimensional patterns of these ones. Also, they can be useful for meta-optics applications and wide variety of applications, for example. And again, hard work of Fang Ren has paid off in getting these unexpected, beautiful results. So now let me talk about the ring resonators I told you. This is Wei Wang, another student who is now doing his PhD with us, and where he has really designed these ring resonators and what should be the diameter of the ring and what should be the width of the ring and thickness of the ring. And he excites these ones and look at the light emission. And you can see that you can look at you can see broad light emission below threshold. Above threshold, you see these beautiful whispering gallery modes, for example. These are experimentally measured ones and these theoretical ones that are matching very well. And again, my colleagues involved in this work have been listed here. And you can also see that below threshold, a broad light emission, above threshold, a narrow line width, and again, threshold-like behavior log-log plot. And again, hard work of Wei Wang is paid off, and we were able to demonstrate these bottom-up grown ring resonator lasers. Till now, most of the ring resonator lasers are top-down etched process, but these are the bottom-up approach ones, for example. So till now, I've only shown you optically pumped lasers. But ultimately, industry wants to see the electrically pumped lasers. And this is the work of Dr. In-Suk Yang, and who worked very closely with my colleague, Professor Lan Fu, and where we are doping these nanowires with a P-type dopant like zinc in the case of indium phosphide. And we grow some indium gallium arsenide quantum well, which is the yellow one here. And then the silicon doped indium phosphide, which is N-type indium phosphide, to create a PN junction. Quantum well acts like a gain medium, for example. So about 2 years, In-Suk spent a lot of time in optimizing various growth processes to get a good quality nanowires with quantum wells. And then afterwards, he transferred them onto the glass slide and then really make contacts and be able to really make contacts using electron beam lithography, for example. Then we inject current and look at the voltage drop, or apply the voltage and look at the current flow. You can see the IV characteristics showing like a nice diode-like behavior, indicating that the hard work of In-Suk paid off, and he is now at a Samsung working in Korea, for example. If you inject more and more current, and then you can see that more and bright light is coming out of these ones. And you also see two emission peaks because of the fact that the quantum well on the top has got a different thickness and composition with respect to the quantum well on the side walls, for example. But you do not see any narrowing of the line width, and you do not see any threshold-like behavior, indicating that these are acting like a nanowire LEDs rather than nanowire lasers. You can ask me why. What's the problem? Because you got a PN junction, you made some good contacts, and it's behaving like a diode. It turns out when you put metals on top of these nanowires, they got huge optical losses. Then you create a lossy cavity. You have to pump them harder. If you pump them harder, then you're creating a lot of heat, and heat reduces the gain. You have to pump them even harder. It becomes like a vicious circle. So now you got another student, Nikita Gagrani, who has really spent a lot of time in replacing these metals with metal oxides like indium tin oxide and aluminum zinc oxide and other transport conducting oxides, with the hope to be able to really still inject current and then minimize the losses so that we can make, hopefully be able to make electro-injected nanowire lasers. In-Suk, before completing, And he has also made these added nanowire LEDs, and then he has grown these nanowires, typically using selective epitaxy. And we fill this with a polymer like a PDMS or BCB or SUA, and then we really selectively etch the tips of these nanowires so that you can expose the tips and put some indium tin oxide and the metal contacts at the top and the bottom. Then you measure the IV characteristics, again, diode-like behavior. As and when you're injecting more and more current, you end up seeing the brighter and brighter light emission. And in fact, you can see under the probe a bright light coming out of this one as well. Because it turns out that if you can really, because you're embedding these nanowires into this polymer, you can be able to peel these things off and then be able to really use it as a flexible LEDs. In fact, Nikhil Ragrani has really spent, as a following student, has spent a lot of time in making these things to work, and we just published his work most recently in Nanoscale Horizons or so. So why are we interested in flexible LEDs? Flexible LEDs are very good for foldable phones and foldable computers. Also, Apple and Samsung and others are interested, so that's why we're exploring these ones. So now let me move from lasers and LEDs to terahertz radiation. Terahertz radiation falls between electronics and photonics. And as you can see, this is 1 terahertz is about 300 microns in wavelength. Why are we interested in terahertz radiation? It turns out many of the chemical molecules have got signatures in the terahertz parts of the electromagnetic spectrum. I'm giving an example of a lactose, monohydrate, and anhydrate. Many of the explosives have got signatures in the electromagnetic spectrum, in the terahertz part of the electromagnetic spectrum. Also, terahertz radiation is reflected by metals, and also you can use them for biomedical imaging applications, for example, looking at the cavities in the teeth, and also for wireless communications and detection of water content in the leaves. And most importantly, terahertz radiation is a non-ionizing radiation. That means it doesn't create any damage to your DNA, unlike X-rays, which are ionizing radiation, for example. Again, this is work jointly with my colleagues at Oxford University, Professor Michael Johnson, Professor Laura Hertz's group. This is the work of my student, Dr. Kun Pang, who is now a postdoc at Oxford University. Kun has really transferred these nanowires onto quartz substrates and then use the electron beam lithography, made some contacts, and then you excite these nanowires with the laser pulse, and then you really come with the generate photocarriers in these nanowires and come with the terahertz pulse. And the electric field of the terahertz pulse is the one which separates these carriers, and then you can measure the photocurrent as a function of time. If you can measure the current as a function of time, you can extract the electric field as a function of time and also conduct it to the material which you're dealing with. Again, to cut the long story short, and Kun Pang, working very closely with Professor Lan Fu during her PhD, she has demonstrated these beautiful gallium arsenide or indium phosphide single nanowire terahertz detectors. And we grow these nanowires using selective epitaxy, which I've shown you. We transfer them and create some antennas or bow tie antennas, and we connect these bow tie antennas with a nanowire here, for example. Okay? These nanowires are about 8 microns long. Okay? Then we again do the same thing as we have done in the past, and then you can see that when you can measure the electric field as a function of time for a nanowire detector and a simulation expected, and then the bulk reference, they all look very, very similar. If you take the fast Fourier transform of this time domain signal, you end up getting the frequency domain. You can see that these nanowire detectors are also have got a broad bandwidth as simulations are predicting, and very much close to the bulk reference nanowires as well, the terahertz detectors as well, indicating that these nanowire detectors are excellent. Particularly, these are operating at room temperature. You can measure both amplitude and phase. So now, during the last 3 years as a postdoctoral fellow at Oxford University, Kun Pang has really looked at how can we really create a polarization result terahertz detectors. And instead of having one set of these bow tie antennas, and she tried to put another set of bow tie antennas 90 degrees to each other, and then try to put nanowires at the top and the bottom as well. The challenge has been to avoid the contact between the top nanowires and the bottom nanowires. Again, working with our Stafford colleagues and Oxford colleagues and ANU colleagues, she was able to fabricate these ones over a 3-year period or so. So what are we doing with these ones? Well, we've been exploring and then seeing where we can make use of. For example, we are studying the terahertz metamaterials. You can design and fabricate a terahertz metamaterial. You send a terahertz pulse to this terahertz metamaterial, and then it interacts with the metamaterial and changes the polarization state. So now you can really use our detector to be able to measure both X and Y polarization, for example. So this, in fact, Kunpeng has designed and fabricated these terahertz metamaterials, and her designs show that the X and Y polarization should have this type of transmission. And in fact, our detector is being used to be able to measure these ones. And then, in fact, we published this work 2 years back or so in Science, and Kunpeng is thrilled because her hard work really paid off. And particularly, she's keen on coming back to China, for example, as for a faculty push. So beauty of these ones is that these are the room temperature operating, polarization sensitive, amplitude and phase sensitive detectors, which we are now making use of them for creating high resolution terahertz imaging systems for biomedical imaging applications and security applications as well. And then we've been thinking about where else we can make use of these nanowires. And this work of Dr. Xian Li, my young colleague in the group, and then where she has been looking at the resonances in these nanowires. Just look at if we change the diameter of the nanowire, and then what happens to the absorption process of these nanowires, for example. You can see essentially by changing the diameter of the nanowire, we can change the resonant wavelength. That means you'll be able to detect different colors of light, for example. Based on our simulations, and we have really grown these nanowires of different diameters and then fabricated these detectors. You can see that these photocurrent as a function of wavelength. You can see that by changing the diameter of the nanowire, you can be able to really tune this detection wavelength. And this really provides opportunities for us to be able to make these multi-wavelength or multicolor detectors. And in fact, working with my colleagues at the University of Western Australia with Professor Laurie Ferroni's group, we're able to take this flower and then be able to image it with our detector and be able to produce excellent quality results from that point of view. These will be very interesting for multispectral analysis, for example. We're developing some particularly focusing on dual band multivalent detectors, for example, in the visible region as well as infrared region. So before closing off on these photodetectors, and most recently we have created some heterojunction photodetectors, and by two of our young colleagues, Dr. Yi Zhu and Dr. Vrs. Dr. Yi Zhu now is a postdoc at Cambridge University. Dr. Vrs. is a postdoc at Glasgow University. Both of them, by working together, we've been able to really make a single photon level photon detection, and where we were able to demonstrate these ones operating at 700 nanometers using a picosecond laser also. Okay? Most interestingly, these are the self-powered devices. That means you're not applying any bias. Because of the fact that they get a PN junction and they got a self-bias, and then the built-in potential is sufficient to be able to really allow us to be able to check these ones, for example. So now let me move towards other topics of nano solar cells. And again, it turns out nanowires are very useful for making solar cells, and they have got low reflection losses, and they acts like a light funnels. You can also create these so-called core shell nanowires, thereby you'll be able to really make the nanowires as long as you want to absorb all the sunlight, and then the core shell really be able to collect the carriers efficiently. Again, we have done a lot of simulations to identify what should be the diameter of the nanowire, what should be the height of the nanowire, what should be the diameter to pitch ratio, and based on these simulations, and we have fabricated these particular nanowire solar cells. Again, this is work of Dr. Vrs. along with my colleagues, closely working with Professor Lan Hu and all others as well. And so really is able to make this P-type indium phosphide nanowires grown by MOCVD. And then we coated these ones with the N-type zinc oxide and aluminum zinc oxide. And then based on these ones, and we were able to really fabricate these solar cells, and these solar cells are showing efficiencies as high as 17% or so. One of the advantages of this one is because, again, in this case, we can fill this gap in the nanowires with a polymer. You can be able to peel these things off so that you can be able to create these flexible solar cells, which in the future, we should be able to really provide you to be able to attach to a backpack, you can be able to charge your phone and electronic devices while you're traveling, for example. It really opens up a lot of opportunities. And also, these are only initial results. There's a lot of opportunities for us to be able to improve these ones further as well. Water splitting to generate hydrogen. While solar cells are very good, but the energy storage is a major issue. But it turns out hydrogen is a clean, transportable, and storable energy source. This work has been led by my colleagues, Dr. Shivakar Turi and Professor Ho Tan, and where we are doing something called photocatalysis. We take a semiconductor as a photoanode, and we take a metal or another semiconductor as a photocathode, and we shine light on top of this photoanode to generate electron-hole pairs. Holes are going and oxidizing water to generate protons, and then electrons are going and combining with electrons to be able to generate hydrogen here, and oxygen is generated here, for example. And one of the challenges with all these electrodes is that the efficiency of the electrodes and stability and cost. Some electrodes are efficient but not stable, but some electrodes are stable but not efficient. And if both are those things and the cost is very high, and then we are trying to work on it, really focusing on all three of them, for example. Just to give you one example of gallium nitride nanowires and nanorods, and this is the work of Dr. Reddy and Dr. Liu. And so really in this case, really they made this bottom-up or top-down process of this bare gallium arsenide, taking this one and then etching these ones, and then really try to look at this photocatalysis process, photocurrent as a function of the over potential. And they found that even the gallium nitride, which is very difficult to etch chemically, are getting oxidized. And they had to coat this one with the cobalt oxide as a co-catalyst and also as a surface passivation layer. And there we were able to show that we can be able to stabilize this one very well, for example. But still, gallium nitride is not the best material because it doesn't absorb the visible light. We're exploring indium phosphide and other wide variety of materials as well. And we're also looking at wide variety of top-down etched nanowire arrays, and which I've already mentioned about gallium nitride one. And again, in a similar way as that of the patterning, as which you use for growth. And in this case, instead of using these patterns for growth, and then we end up using them for etching, we're using etch mask or so. And thereby we'll be able to create this large area of these nanopillars, for example. This is the work of our student, Xiyu Wei. And so she's been really developing these things for sensor applications, for example. So really, we were looking at these sensors. Again, Professor Lan Fu is leading this particular program. There we are coating these nanowires selectively only by glancing angle deposition of gold and be able to make good contacts or so. And then we are really measuring the response of these nanowire sensors. And so essentially looking at NO2. And so we'll be able to detect this one. And we'll be able to show that you can really detect as small as 3.1 ppb in operating at room temperature with high selectivity. Because lots of times in the sensor case, then we'll be detecting more than one gas. So that means it becomes a bit more challenging to identify which gas it is detecting. You can see that Xiyu has shown that you can is only detecting NO2 and all other gases it's not able to detect, for example. Also, these sensors are also working at room temperature. Lots of times, many sensors are really heated to high temperatures, but in this case, you don't have to do that one. And it becomes much more convenient to be able to do that one as well, for example. And we've been exploring a wide variety of nanowire sensors, and which I will not have time to go into the details. Let me finish off with the last topic of brain repair. This is the work of Dr. Vinny Gautam, and then as most of you know that we got about 80 billion neurons, and then these neurons form into neuronal network. So whenever you get a brain damage due to accident or one reason or neurological disorders, you're breaking these neuronal networks and you lose some of the functions. Can we create a neural patch and then be able to make these connections back and then be able to really create, help people those be able to recover their normal life, for example. This is a question which we asked ourselves about 5 years back. And Dr. Vinny Gautam has spent a lot of time. She's now a lecturer in biomedical engineering in Melbourne University during her period in ANU as an young colleague. And she's grown these nanowires, these neurons on top of these indium phosphide nanowires, which are using the top-down process again here. And then you can see these neurons, these neurites really follow these patterns beautifully. These are particularly axons or so, including dendrites here. So what we do is that we take these ones and so look at, we've grown these multiple neurons, and you can see in this box region is where the nanowires are, and these neurites really follow these patterns beautifully. What Vinny does is she does something called calcium imaging. As and when these neurons are firing, opening action potentials, ion channels gets opened up, and then in the process, the calcium dye fluorescence changes. It depends on the calcium ions concentration. And then Vinny does this correlation maps of if this neuron is firing, what's happened to this neuron and this neuron and this neuron. And then she compares these neurons grown on nanowires with nanowires which are grown on neurons grown on plain glass substrates. We can see when the neurons are grown on plain glass substrates, change in fluorescence as a function of time. They're all randomly firing, indicating that very little communication is taking place between these neurons. But with these neurons which are grown on nanowires, they're all firing all at the same time, and then you see excellent correlation coefficients, indicating that there's some sort of a synchronized and correlated activities taking place. And when she presented his work about 4 years back at a neuroscience conference in Melbourne, neuroscientists were asking what neurons you're using. And then she said that she's using mice neurons. And then she said, they asked, what about using human stem cells? So now we got a project, in fact, funded by the Dementia Australia Research Foundation and Gilbert Foundation. And so really, we are taking these stem cells from the Alzheimer's patients and then using the CRISPR technology, Cas9 technology, and make the so-called organoids or mini brains with and without microglia, and really measuring the signaling differences with the nano electrode arrays, as well as the calcium imaging, and applying the deep neural networks to analyze the data from understand what are the signaling differences between Alzheimer's patients and healthy people. And also in the future, we want to be able to really introduce some drugs and then see how can we be able to recover the signals back from the Alzheimer's organoids, for example. So in fact, we developed these nanoscale electrodes and arrays, particularly this work of Dr. Raj, and who is really spent a lot of time in developing these nanoscale ones, which allows us to be able to measure single neurons as well as the neuronal network, and really plays an important role. So this really project involves neurobiologists, stem cell biologists, computer scientists, and us as nanotechnologists. And really, we're learning a lot and working with each other, learning from each other. It's an exciting project which has got a great potential. First, if you want to really find any cure, first you have to understand the disease and its functioning, and then see how we can be able to improve the health of the human beings, for example, particularly aging population. In conclusion, nanowires open up opportunities for manipulation of light matter interaction at the nanoscale and developing a new class of lasers and LEDs, infrared and terahertz detectors, integration of optoelectronic devices on various platforms, and solar cells and PEC water splitting, and sensors, and also engineering the growth of the neural networks. It really opens the sky is the limit in terms of what you can do with these particular structures. Okay. With that, I'll leave you with some information. Professor Lanpu has already mentioned about applied physics reviews, and whenever you get a major breakthrough or original research, and then please think of us. And our Center of Excellence advertises positions for PhDs and postdocs whenever they get an opportunity. Please keep an eye on this one. And also, they've got 5 university partners are there, and hopefully it'll get you the opportunity. And again, to help support students and young scientists from developing countries, my wife Vidya and I have started an endowment, because there are lots of bright people in the developing world, but they don't get many opportunities. And we want to really open the doors for them and to enable them to be able to come to Australia and spend some time at the ANU, for example. With that, I want to thank you for your attention. I'm happy to answer any questions you may have.
Thank you very much, Jagadish, for a wonderful talk, as always. We've got a few questions from the audience. Maybe I'll start from a bit more technical one that you can clarify, and then we go to the more general ones. So the first question is saying that, Professor Jagadish, I assume all this work are based on silicon substrate. Did you try other substrates, especially can it be flexible?
Okay, that's a very good question. Thank you. First of all, we are not using silicon substrates. We are using 3-5 semiconductors like gallium arsenide or indium phosphide. We've also grown these nanowires on silicon substrates as well, but we have not done as much work in that area than what we have been doing based on 3-5 semiconductors. The second thing is that it turns out that these nanowires can be bent much more easily because of their smaller diameters, and we can introduce strain as much as 10% or so. In fact, we've done these measurements in a transmission electron microscope and then applied some pressure and then seen how they are behaving. And really, these are very good for flexible optoelectronics as well as electronics as well. And that's what we're exploring, of using them for flexible LEDs and flexible lasers, and as well as also flexible solar cells and range of applications. And hopefully, we'll be able to make in the future flexible sensors as well.
Thank you, Jagadish. Maybe I will follow up with this question, because I have been also asked a lot about, do you really think that without silicon substrate, there's no future for 3-5s? Because people really always say that if you can't demonstrate 3-5s on silicon, it can't be really implemented in the industry. So what's your view?
That's a very good question. That's a very good question, Pulan. And in fact, that is why, it's a really pleasure to see, companies like IBM Zurich has been spending a lot of time in growing 3-5 semiconductor nanowires on silicon which are already in the industry process they've used on a 6-inch silicon wafers, for example. It is not in the laboratory in the university, this is in industry, and where they have shown excellent performing indium gallium arsenide based transistors. Reason being that 3-5 semiconductors, not only they are direct band gap semiconductors, they've got a higher carrier mobility. If you want to make fast transistors, it is better to make use of 3-5 semiconductors than silicon. So that's why IBM has got a lot of interest. Yes, I agree with you that it's important to really combine both of them. And that is where the nanowires have got a particular advantage, because the lattice mismatch is not a major issue. And unlike in the two-dimensional materials where the defects have always really created a lot of problems for us, we can get over that one by combining both of them. That's something which, in fact, I always ask my students and postdocs, you're doing all these wonderful things, unless otherwise you're really not able to make it on silicon, really it's not going to have an impact. And then they keep on trying. And then I'm hoping that one of these days they will demonstrate beautiful lasers which are on silicon and also other devices as well. I agree with you that silicon substrates really are going to play an important role that also can reduce the cost as well.
Yep, thanks, Jagadish. I've got another question from Xin at Chongqing. Professor Jagadish, so glad to see your wonderful work. I'm working on Optoelectronics too, but it's really hard for us to get good control of doping in carbon nanotubes. Any comments on this?
So it's a very good question. Of course, we're not particularly working on carbon nanotubes, but the challenge with most of these nanostructures, the doping challenge is always a challenge. In fact, even how do you measure the dopants in these structures? Because of the fact that you cannot use SIMS measurements or Hall effect measurements and all these things, unless otherwise you make a large diameter structures. And that's where we've been using terahertz conductivity measurements or terahertz spectroscopy to be able to measure the conductivity of these nanostructures in a non-contact way. Because again, if you put metal contacts and other things, contact distance also can play an important role. That means you don't know what you're measuring is coming from the contacts or the actual material. So one of the other challenges which you point out is that, because of the fact that the surface is close by, then introduce the dopants. And then what happens is dopants even prefer to come and segregate outside surfaces. And that's where you need to get over that particular problem by really trying to do this, not go to the thermodynamic conditions. Maybe you need to find some kinetic conditions where you'll be able to introduce the dopant, for example. Just to give an idea, that we are not able to really get a high carrier concentration P-type doping, because mostly you need to do this once at low temperatures. If you do it in low temperatures and the quality of the material is bad, and then you have to compromise, you have to go to high temperatures to get a good quality material. In those cases, zinc doesn't get incorporated that well, otherwise it comes off, for example. Okay, so that's where always a challenge when you're dealing with these nanostructures dopants. And one way possibly you can do that one is that you can do the core cell structures and then be able to really create the dopants in the nearby so that you can get the so-called modulation doping, for example.
Thank you. There's a question about water splitting. You mentioned of using 3,5s material for water splitting and energy storage, but 3,5s is generally quite expensive. And to be able to do large scaled manufacture, what do you think the application of 3,5s in this field?
So that's a good question as well. But mainly we're using 3,5 semiconductors to test the ideas which we have, for example. And then see, what materials, can we really be able to make efficient structures, because we've been using these optoelectronic devices. And again, in the photocatalysis, all these things which we're learning and doing things in the solar cells and other things, the same physics applies there as well. But we're also moving towards away from 3,5 semiconductors as well, particularly in the case of the water splitting, because the cost is a major issue. Not only dimensions and cost, both are a major issue. And so that's why we're really exploring other materials other than 3,5 semiconductors as well. But 3,5 semiconductors are allowing us to be able to test the ideas and then try to go and then reduce the cost and then scalability. And that's where we are moving towards other materials as well.
Thank you. I've got a last question. It's a more general question from Lily Zhang at Shenzhen. Dear Professor Jagadish, thanks for your great talk and so many distinguished achievements in academy. I want to know your opinion about commercialization of research output. As a young faculty, I'm really struggle on my research's real value. Thank you.
Oh, that's a very good question. So this again, particularly nowadays, all the governments are really expecting those of us, those are working in the universities or institutes to really commercialize our technologies, our research which we are doing. The key message is to me is that you need to have the full spectrum of research. You need to have fundamental research, and then you need to do applied research, and then you can do commercialization as well. But then you should not focus on just on commercial research, and that means you really lose the opportunity to be able to build up the next generation of pipeline of ideas and then verifying their suitability for developing technologies, for example. So my advice always is that we need to do the fundamental science. Fundamental science is really for the foundation for the developing of the future technologies, like building a house, and without foundation, you cannot build a house, and it will not stay for long if you really even build one. And the same thing applies here as well. So depends on what you want to do. See, some people want to do fundamental science and they want to stay in fundamental science, and some people want to do applied science and want to really move towards technology. And depending on your interest, you can do all three of them as well. And then you need to focus on what is your area of strengths and what makes you happy. At the end of the day, you have to have fun with what you're doing. Okay? And of course, you need to also understand what is expected in your system as well. If in your institution, they are asking you to focus on more fundamental aspects, if you do applied work, you won't get appreciation. But if they're expecting you to do applied work and then you're doing only fundamental work, it doesn't help. And you can do balance these ones as well. In fact, that's what we do. In our group, we try to do some fundamental work, and then we do some applied work, and we also transfer some of the technologies to industry as well. And in fact, 20 years back, we started a company called Acton Lasers to commercialize some of our laser technology, but suddenly market collapsed, and then we had to close the company, for example. But then now I work very closely with my colleagues and try to work with industry and collaborate with them. It turns out, if you talk to industry, and you learn about what is the actual problems they're facing. In the universities, our institutes, we like to solve the problems. Instead of solving imagined problems, by talking to industry, we can solve the real world problems, for example. Just to give you one example, most recently, when we were really demonstrating these photocatalysis electrodes, for example, and most of the time when you're writing papers, you really publish these ones with the 10 milliamps per cm square current, and that's more than sufficient to write a nice paper out of that. When we spoke to industry, they said they wanted to have 500 milliamps. That means 50 times more. So then they wanted us to show that they're stable at those currents. So then it really made us to think and then come up with the right technology, and we were able to demonstrate that one. So now they gave a big contract to us, and my colleague, Dr. Shiva Karuduri, is leading that one, for example. So there are some advantages of working with industry, but at the same time, you need to also have your core competency and then continue to do your own science, which you're enjoying that as well. You can balance these things carefully.
Thank you very much, Jagadish, for joining us tonight to deliver this excellent plenary talk. And thank you very much. And I think I'm now going to hand the microphone back to Alice again to our next talk.
Yes, I'm waiting here. Thank you very much. Actually, Professor Jagadish, may I ask you the last questions? Okay. Sure. Yeah. I'm so proud, we are partners on iCANX, the stage for, almost 2 years. And now you are going to be the president of Australian National Academy. I hope I use this last chance to ask you to deliver some encouragement to the audience, on iCANX. So is that possible? You say a few words to encourage the people worldwide, here.
Thank you, Alice. And the iCANX program has been fantastic. And as you know, that millions of people have been listening to these talks. And again, it is important for us to be able to reach the public and then be able to share the excitement of science. In order to do science, it's a public, and the society gives us a license to do science and supports us as well. So that's why you got the responsibility to really communicate and share the excitement of science and what we are doing with the investments public is making for us to be able to really have fun doing science, for example. So that's why this iCANX program has really changed the community quite significantly during a pandemic time when we were not able to meet. And Alice Zhang has really come up with this brilliant idea. And then she's got enormous amount of energy. And then she really makes everything happening. And then really she invited me and Professor Paul Weiss and Martin Tho, and then of course now Professor Lam Pu, and really creating this wonderful program. And then I encourage you to really listen to these iCANX talks every Friday, 8 p.m. In Beijing time. And then I hope you'll benefit from these ones because the speakers are really outstanding. And then they're leading experts in various fields. And then this really broadens your horizons. It may allow you to come up with new ideas and be able to also explore new research areas as well by listening to these interesting multidisciplinary, interdisciplinary talks as well. Congratulations, Alice, and good luck to you and the rest of the team as well.
Thank you, Professor Jagadish. We are so proud of you. I hope almost next week, right? You are getting into a new position. Yeah, you got all our support and all our best wishes. Yeah, we hope we can collaborate in the near future. Okay, thank you, Professor Jagadish.
Thank
you very much.
Bye bye.
Yeah.
Thank you.
Okay,
Bye-bye.
thanks. Yeah. Actually, this was our first plenary talk on iCANX, summit this year. We are really proud we have Professor Jagadish here. And then next we're going to have another very important, people on this stage. Yeah, here I tell everyone， 我开场的时候已经说，我为什么会穿今天这件 T 恤衫呢？对，带着中国的字样呢，因为这是中国奥运会征战的 T 恤衫啊，我非常幸运的有一件。这个 T 恤衫呢也非常的有故事，当然这个故事呢，我就希望你们听完下一个这个 speaker， 这个我们大会报告人的报告以后，我再来揭秘为什么我有一件这样中国征战奥运会的 T 恤衫这也是一个非常有意思、非常动人的故事，科学、艺术和体育相结合的这样一个故事。那所以呢，由此呢带来今天下午的这个 talk 今天晚上的第2个 plenary talk 大会的报告呢，非常的独特。当然，我要请一个特别独特的人来引出我们的 speaker， 那就是陶光明。对，有请陶光明老师来介绍我们的下一个 speaker。陶老师，请。
好，谢谢海霞老师，非常荣幸有机会作为我们 iCANX 大会报告的主持人。接下来我向大家简要介绍一下我们洪平教授。洪平教授从92年开始在北京体育大学攻读这个运动相关的专业之后的职业基本上都是在我们体育总局科研所，包括这个国家队相关的一些这个工作经历，科技助理工作。所以我们洪平校长是一个非常专业的一直在我们体育的一线进行科技助理的这么一个专家。尤其在我们北京冬奥会上我们洪平校长是担任我们冬季运动管理中心的副主任，也是我们负责处理整个我们冬奥会过程中的科技助力的总协调人。在去年12月份的时候，洪校长调任了北京体育大学担任副校长，目前是在做备战巴黎奥运会的办公室常务副主任。洪校长在过去的工作时间以来，主持了各类的省部级课题30余项，获得了省部级以上的奖励13项，其中包括国家科技进步2等奖1项。洪平校长接下来将给大家来分享助力北京冬奥会背后的科技故事，非常值得大家的期待。好谢谢大家。接下来把时间交给我们的洪校长。
各位老师、各位专家、各位朋友们，大家晚上好。我来向大家做一个北京冬奥会中国冰雪科学训练体系的介绍。北京冬奥会我们为什么要去申办它？北京冬奥会是人类历史上第一次从寒带地区到温带地区，第一次从高纬度到中纬度，第一次从发达国家到发展中国家。它与我们中华民族的伟大复兴和我们的2个100年的交汇的历史时期非常契合，所以总书记亲自谋划、亲自推动了北京冬奥会的申办，并且获得了成功。那么北京冬奥会我们要取得什么样的成绩呢？我们来看这张表。美国02年盐湖城参赛率100%， 80年美国普莱西德湖参赛率100%。2017年我调到国家体育总局东艺中心参加了平昌冬奥会，韩国人平昌冬奥会参赛率82.4%，平昌冬奥会中国代表团只参加了52%的项目，意味着有48%的冬季运动项目、奥运会项目我们没有参加，我们没有教练，没有运动员，没有场地，没有知识，没有器材，没有装备，我们该怎么办？我们只能通过全项目建队。怎么建？ 我们通过跨界跨项选材，从武术、从杂技、从夏季项目等等各种项目，把我们的人才选上来。我们要全项目训练，我们的全项目训练包括了我们的4季训练，包括了我们的模拟训练，包括我们的专项训练、出国训练。我们要全项目参赛，我们要参加各种比赛，获得国家积分，取得国家资格，才能够参加奥运会比赛。我们要全领域备战，包括厨师，包括我们的安保，包括我们的防疫，各个领域全员来备战。我们还要全链条保障我们的营养、我们的心理、我们的器材、我们的装备等等。我们要实现这5个全面，我们有赖于来补齐我们的短板。我们最大的短板是什么？我们最大的短板是科学化训练。所以我今天晚上的介绍就会围绕着这一幅图的结构来展开，围绕着人、机、环3大要素的整合来进行我今天的这个介绍。我们先看这么一个视频，这是一个雪橇项目的比赛，左边是时速，右边是它的旋转方向，这个地方是它的这个身体重心的所承受的载荷，这边是左右的方向，开始加速，可以看到它的速度越来越快，在拐弯的时候，它的重力加速度达到了5个 G， 身体承受压力到了400公斤，最高时速已经达到了120公里每小时。
Kurve, die höchste Geschwindigkeit so die 125 Kilometer pro Stunde durch den Kreisel und gleich hinein ins Labyrinth. Unglaublich jetzt auch die Gehwerte. Schauen Sie doch mal auf diese. Da, über 5 muss man da aushalten. Da die Orientierung zu wahren, ist ganz, ganz wichtig. Und jetzt nähert sich der Schlitten bereits dem Ziel, das jetzt erreicht ist. Ja, und wenn das keine Dynamik hat, danke Julian von Schleininstitut an der Uni.
大家看，这是雪橇项目，它是躺在这个车橇上，它基本上看不见前面，它的身体要承受5个 G 的载荷，而这和我们的飞行员，特别是战斗机飞行员的载荷相类似。它的最高时速能够达到125公里每小时，所以它的训练方法就不是一般意义上的训练方法，它需要用飞行员的训练方法来进行。在这个过程中，人所受到刺激最大的一个要素来自于载荷。这是一个钢架雪车项目，大家看，这个运动员不是仰着的，他是趴着的，它的最高载荷能达到8个 G， 相当于战斗机加速的载荷。8个 G 乘以这个体重100公斤，体重的话，有可能它的整个载荷达到800公斤的这个压力。这是我们的雪车项目，雪车项目长成这个样子。那么它的最大载荷能达到5个 G， 这个也是相当强大的。那么在这个载荷过程中，胸背向载荷对人体的影响，它会对呼吸、对肺活量、对血氧饱和度产生重要影响，对我们的血压、动脉血压以及我们心脏功能和工作效率产生损害。同时，这样的比赛，冬季项目的雪上比赛，一般都在海拔1500米到2000米的这样一个高度。那么这个高度的环境对我们的内分泌、心血管、神经、血液、呼吸、骨骼肌等诸多系统都会产生影响，同时这些影响都是在-20度左右的低气温下产生的，所以在这个过程中，人所承受的运动的压力、承受的环境的这个压力是可想而知的。所以我们在整个过程中，我们的研究问题主要围绕着人，什么样的人来进行训练，这个人开展什么样的运动，比如说雪橇还是高山滑雪还是越野，运动中的人，运动中人的载荷、血压、血糖以及各种能量代谢等如何分析，人在环境中的运动，人在海拔地区低氧，人在低温环境中的运动，这是我们的4个研究的方向和问题。其中最核心的问题是什么？这是我们所有运动学的最核心的，力量等于质量乘以加速度，没有力量就没有加速度。我们可以看博尔特是全世界全人类跑得最快的人，他的肌肉，他的身高快2米了， 所以它这样的力量能够支撑它跑出9秒58的百米成绩。我们再来看马龙卧推230公斤，乔丹200公斤，而我们中国的很多篮球运动员可能卧推只能达到120-130公斤，这种差距在力量上的差距就凸显出我们的短板在哪。那么根据我们对项目的生物力学分析，我们要提高动力。那么这个动力如何提高？首先是进行体能训练，强化动能；第二个是进行技术训练，使我们获得的动能有效利用。根据数学模型、生物力学分析，我们得到这样的一个数学模型。基于数学模型，我们应该从肌肉功率和运动链和核心力量训练群以及这个能量驱动如何优化我们的整个技术，来突出我们有效利用体能整一个全套环节来提高我们的动能。同时动能提高了，那么阻力呢？我们要减少阻力，动力提高，阻力减少，合力才会增加。那么在阻力方面，我们遇到的气动阻力占90%到70%，地面摩擦阻力在30%到10%，其中气动阻力里面的形态阻力占非常大的比例，而形态阻力里面和运动员与装备之间的气动干扰，运动员身体的姿态的干扰占比较大的阻力。所以我们对阻力进行分析以后，找到重点，这些重点集中在减少阻力、提高成绩相关的服装、装备、人体运动以及技战术动作的优化方面来开展。那么把刚才的问题把它合成为人的要素、装备的要素和环境的要素，如何提高动力、减少阻力，来提高我们的运动表现。那么基于这样的分析，我们要对标世界的训练赛场，对标国际的训练体系，高点定位，通过多学科的交叉来使我们的成果进行集成，通过高水平的教练员和多学科的融合团队来保障我们整个系统从数据采集、分析到训练指导和训练设施方面开展大协作，来提高我们成绩的突破。这是我们整个的框架的设计。围绕了人，我们首先对我们的运动员进行基因的检测和分析。这样的基因检测和分析可以把运动员的运动潜能、营养代谢、运动损伤和相关的维生素、矿物质的代谢搞得一清二楚。到底这个运动员适合力量，还是适合练速度，还是适合练耐力？然后基因分析完以后，我们对运动员的动作进行动作模式筛查。动作模式筛查可以提高动作的效率，可以减少运动的损伤。然后做伤病风险的排查，看看它的薄弱环节在哪，我们如何进行优化训练来提高、减少、来降低受伤的风险。同时进行力量数值测试，把力速曲线测出来，知道运动员在什么力量下以什么速度是最有效的。进行能量系统的测试，把它的最大摄氧量和无氧功测试，了解它整体的内部代谢的机制是什么，效率是什么。进行体能训练，通过数字化的体能训练中心的打造，配备多种力量训练装备，使运动员的训练得到有效增强。同时在训练过程中，对运动员的训练负荷进行监控，这个监控有内负荷也有外负荷，这是用心率监控它的内负荷，同时还有速度、力量监控它的外负荷。基于监控以后，我们可以通过血液学测试，测试它的肌酸激酶、血尿素、睾酮、皮质醇等等生物化学指标，来了解它的疲劳状态，来调控它的训练。我们定期对运动员身体成分进行测试，看它的肌肉含量和脂肪含量的比例，以此来优化它的营养供给。那么营养供给，我们这是数字化的餐盘，每一道菜它的碳水、它的脂肪、它的蛋白质供给是多少，然后每一盘菜下来以后，每个运动员摄入多少能量，他每天训练消耗多少能量，然后能不能把它做到有效的平衡。所以我们说营养也是战斗力，吃饭也是训练。对运动员的所有数据进行分析，对他的技术动作进行优化，来提高他整体的动作这个效能。同时运动员训练完以后，通过微压氧舱、通过漂浮舱这样的装置来进行运动员的再生恢复。 使运动员练得疲劳，同时恢复得更快，一天能上2个强度，一周能上多个强度，使我们单位时间里面的训练效益最大。所以我们把再生恢复的目标、手段和控制指标进行匹配，然后高强度训练后的恢复方案、耐力训练后的恢复方案、力量训练后的恢复方案，我们按整体的流程来操作运动员训练完以后的恢复，使他训练快、恢复快、效果好。在这个过程中，我们对运动员进行脑电心理变异的监控，来进行心理咨询，确保运动员的心理状态保持一个好的这个水平。每天晚上的睡眠，我们通过大数据加人工智能的这个方式，通过这个传感器来获得运动员的相关睡眠的指标，对运动员的睡眠健康进行监控，来评估他的训练效果。运动员有伤病，那我们给他进行声光电热冷震动磁等等的刺激，使运动员的小伤小病能够在我们的康复工作站得到尽快的康复。如果运动员有大伤大病，那么我们给他建立了绿色通道，让运动员能够快速的在现场或者去医院接受有效治疗。这里面要专门说一下，冰雪项目是一个高风险的项目，同时在高海拔缺氧、低温，因为是在高海拔这个低温状态下，所以它很多医疗条件不具备，所以它是一个弱保障的这个项目。所以我们围绕着救治体系，全流程、全专业、全要素、全地域、全人群、全社会开展救治体系，围绕着防、诊、治、控、康5大环节，把预防、手诊、中西医结合、常态化监控和多手段康复把它整合在一起，通过智能化的5G， 通过精准化的康复，通过个性化的护具研发，把我们的科技手段和我们的医疗保障整合在一起，同时打造我们的零容忍、零出现的反兴奋剂的这个平台，使我们运动员零容忍、零出现，保障我们参与冰雪运动的纯洁。这是我们全社会总动员的绿色通道，这是我们建立的这个全流程的这个保障，从直升机转运到现场的保障，到远程的会诊。这个是我们的数字化这个医疗档案，这是我们的5G 技术在这个整个救治中所发挥的这个功能。这是人的部分。那么关于装备方面，这是一双鞋，这双鞋从提出来到最后实现参与到比赛用了3个月。我们的安踏集团，我们的苏炳添的专项教练，我们中国冰雪的首席科学家，我们很多专业的同志们共同奋斗3个月，产生了这么一双冰上这个雪车雪橇的跑鞋。这双跑鞋空气降低风阻10%，回弹率高达82.6%，它比市面上卖的大牌整个重量要轻15%。这个3D 打印钛合金的钉鞋是全行业首创，每组作用力增加400牛，所以我们运动员穿这双跑鞋，平均起跑时间提高0.054秒，平均提升0.023秒。而这个比赛，如果大家看过以后会知道，0.001秒就是金牌和银牌的区别。而我们通过这样一双鞋，就能够提高我们的动力。所以通过这样的一个鞋的设计，我们打破了欧美体育品牌的垄断。这是我们的服装，这个服装是北京服装学院刘丽教授的团队来主持实施的，围绕着更快的服装、更安全的防护的服装、更温暖的服装和更有文化气息美的服装来开展。我们把中国运动员的体型和技战术相结合，把体型和剪裁进行优化，同时研究自主知识产权的这种材料和结构，把它进行 AFD 的数字仿真计算，计算完以后形成不同的结构的组合，在风洞里面通过人台和实际运动员的尝试，通过风洞来吹出最优的服装面料和剪裁的组合，来达到快，同时把中国文化的元素这个融入到我们的训练和比赛服中，来体现出中国文化之美。 这是一个视频，大家可以看看整个服装的研发过程。这是整个过程。然后基于这样的服装整体的设计，我们的速度滑冰比赛服减阻率这个下降11%，短道服减阻率这个下降10%，高山服装的这个减阻率9%，钢架学车在3%到5%。所以仅仅通过服装的改造，我们对整个成绩的影响都取得了非常好的效果。这是我们的头盔，头盔通过微型结构的优化来提高我们整体的减阻效果。你看，我们有2款头盔，一款减阻提高4%，第2款减阻提高8%，它们在奥运会过程中都得到了有效的应用。这是我们冰刀，冰刀侧面通过镀膜的形式使它更坚硬。那么更坚硬的冰刀在跟冰进行摩擦的时候，侧面硬度提升了19%，蹬冰力提高57%。那么这就使我们整个的运动成绩得到有效的发挥。这是雪板，以前雪板是在板底进行打蜡，那么我们现在把蜡通过特殊的蜡笔包裹技术，把蜡包裹到雪板里面去，然后蜡和雪板结合在一起，我们通过底板打磨和底板开槽这些技术，通过我们自主研发的器材来实现新型的自润滑这个底膜的雪板的研发，那么为国家队提供了65副雪板。这是钢架雪车的优化，钢架雪车的优化最核心的是底下这个刃，这个刃的弧度，这个刃的形状，以及这个刃的长度直接和比赛成绩和冰温直接相关。那么通过我们的自主研发的技术，使我们每个运动员都有3D 打印的这样的一些这个刃以及他们的适用的雪车。这是一个国产雪车的研发过程。
冯老师，您怎么不说话了？突然没上了。唐老师、冯老师是掉线了吗？
哎，没有啊，胡老师没有掉线。
我这儿没上。您这个视频没播放。
哎，胡老师，你的视频没有播放。
没有播放吗？哎，我想想看，那我先停止共享，然后再播一遍。
好的。
好。现在行吗？
还是没有播放。
没有播放，那我就这个 我的屏幕共享已暂停。好，行。但是我现在好像是这个 Zoom 出了问题。那我先退出再登录一次行吗？
好的，好的。
好，现在看见了吗？
可以看到 PPT 视频，您放一下试试。
能看见吗？视频能看见吗？
视频没有看，要不跳过吧？可能视频比较大，要不您跳过这个。
好，跳过。这个是我们这个陶光明老师团队为我们国家队研发的面罩，因为我们运动员在零下20度的环境里面运动，它吸入的空气如果特别寒冷，会对肺进行刺激。那么通过新材料和新结构的设计，使冷空气从头部进入，被头部的热量所加热，然后再吸入到这个呼吸道。那么整体来看，运动中面部皮肤温度提升6度，呼吸中吸入的空气温度提高近20度，这样对我们运动员训练和比赛的保暖起到了非常重要的作用，受到教练员的好评。这是机的一部分。那么在环境方面，我们围绕着天气预报，这个是奥运会历史上第一次实现了100米级和分钟级的天气预报。我们可以对风力的方向、风力的大小、环境的温度进行精准的分钟级的预报。这次奥运会我牵头天气预报，那么有3次重大的天气过程被提前预报，为我们的国家队训练和比赛的过程调整提供了重要的这个支持。经过天气预报日积月累的分析，我们对场地进行预测。这是高山赛道，我们把它放到风洞里面来吹，在不同的区域同等风力下，它的风的大小，它不同区域的风力的方向的变化和我们运动员比赛的关系是什么？那么通过风洞的测试，我们能够得到有效的这个预测，为训练和比赛针对性来提供技术支持。那么风洞我们基于运动场景、训练装备和环境要素的模拟，做了5类风洞，有环形风洞，有垂直风洞，有小型的便携式风洞，还有多要素的耦合风洞。这些风洞为我们的训练提供保障。这个视频看得见吗？
这个视频也看不见。
我就过。风洞。那么基于风洞和天气预报的预测以后，我们来研究4季训练，因为我们的运动员从17年年底开始训练，4年时间要追赶欧美国家10几年训练时间的运动员，我们只有一年变10年，1季变4季才能实现。这是一个室内的优潮。我们用汗血塑形技术、高温造血技术和独立这个制冷温控技术，来使我们这个室内优潮在短短的6个月就建设成功。这是室内优潮的内部场景。那么运动员1年4季都可以在这个室内优潮里面进行训练。我们的谷爱凌在这里面训练过，那么她的优潮拿到了我们的这个奥运会金牌。这个是跳台滑雪， 我们在这个群山之间找了一个避风的地方，同时这个山包正好和奥运会赛道的弧度非常匹配。那我们在这儿建设世界级的滑雪跳台的科训基地，它是依山而建，我们用了307天就完成了整个跳台的建设，创造了世界跳台建设史的奇迹，为我们整体的训练进度提供了保障。这是一个第一座永久的4季的滑雪大跳台，滑雪大跳台和这个首钢的大跳台的弧度是完全一样的，但是它使用了新型的材料，这个材料就是我们的金针菇技术。我们把雪毯、滚轴滑毯、气垫和焊雪金针菇相匹配，搭建我们的仿真的大跳台。这个是一个雪上技巧的赛道，这个赛道是4季可用的。那么它所采用的这个仿真材料，使它的滑度和滑雪的雪的滑度有95%的相似度。那么在这个上面，我们再铺上颗粒状这个雪的这个材料。这个颗粒状的雪，我们是用磁性材料，非常细，但是它们是有磁性的，所以它可以像雪一样连在一起。我们做了3种不同形状的下雪，这样子1年4季，我们可以把它铺到赛道上来模拟滑雪训练。这是场地方面的这个技术。那么在这个方面，我们把人机环进行这个耦合，我们可以看一下这个视频。这个视频看得见吗？这个视频能播放吗？
这个视频可以。
这是在这个冰场上，我们用3D 的无标定、无穿戴运动姿态重建，来建立我们整个的运动员的训练和比赛的关键数据的提取。然后把它重建出来，每一个角度。这是高廷宇的出发技术。每一灯的速度、长度、角度、幅度都能够及时的把它反馈出来，供教练员和运动员训练完以后来分析。这个技术我们也把它提供给了苏炳添团队，所以大家看东京奥运会苏炳添的100米技术得到了非常大的改善。基于这样的3D 的无 mark 点的动作捕捉技术，来为我们运动员训练提供科学的数据支持。这些所有数据随时训练完，直接3D 重建数据分析，把它拿出来，日积月累，通过大数据分析来帮助运动员提高成绩，优化技术。把所有的环境要素，比如说风力、风向和现场的指挥结合在一起。这是我们自由式空中技巧的教练员在看风力风向的玫瑰图来发出信号，让运动员出发。这是我们跳台的教练员也是通过这样的实时的天气预报的反馈来做现场指挥。这个是在我们的冬季2项的现场，这个枪的这个弹着点和风力风向进行匹配，为运动员较枪，为提高他们的射击准确率提供这个技术支持。这是现场的指挥。那么在这个过程中，我们得到了 6位院士的不同学科的大力支持，包括于梦顺院士给我们提出了极限训练，范伟成院士在这个多偶和风洞上给我们很多支持，仲平院士从航天材料上 T800的材料来做我们的学车，陆林院士从心理学上给我们这个的运动员的保障于建勇院士从服装材料上给我们的指导，还有杨月新院士从运动营养学给我们的支持。在这个过程中，我们一共有146位外籍专家来替我们提供国际这个技术，国内有6位院士、15位科学家和1600多位专业人士全身心投入到我们整个这个技术保障中来。我们发挥举国体制的优点，通过这个国家政策的引导、重大研发专项的支持，52家企业的联合攻关，24个高校的服务，还有25家医院的绿色通道的保障。我们把中国的新材料、生物工程、航天航空技术和机器制造、电子信息技术进行了充分的这个发挥，来提高我们的运动表现，使我们整个系统能够在北京冬奥会这个期间得到有效的这个应用。这是我的整个报告，我的介绍完了，谢谢大家。
非常感谢洪校长的精彩报告，听得非常入迷啊。就是我代表各位听众有几个问题汇集到我这里。首先是来自天津的王老师提了一个问题，说洪教授您好，这次冬奥会非常成功，运动员的状态也普遍比较好，感觉跟你讲的内容非常有关系，谢谢你。我的问题是，这些科学训练手段是不是也适用于足球运动？能不能用来提升足球运动员的体能？
这个刚才我说了，F 等于 MMA， 并且也举了篮球运动员几位 NBA 巨星的例子，他们的力量非常强大，没有力就没有加速度，没有力量就没有对抗。我们冬季项目的突破是高度重视体能训练的结果，是高度重视力量训练的结果，而我们形成的这样一套训练监控、技术诊断、技能评定指导下的力量训练或者体能训练是非常有效的。那么通过有效的高强度训练，我们再辅以再生恢复、康复治疗和心理支撑，那一定会起到非常好的训练效果，而这一套系统一定是适合足球训练的。我们也在努力的把我们所形成的成果向整个竞技体育来推广。我的回答完了，谢谢。
好，感谢洪校长。第二个问题是来自于新民，说洪教授，感谢您的报告。比赛的设备都有标准和要求，比赛的服装应该也有相应的标准。这些微结构材料、新器械的使用，是不是也要经过相关的审查？包括另外一个教授也提出类似的问题，说体育运动器械的改进是不是需要国际体育组织的认定？好，谢谢。
我们研究任何一款服装或者器材，首先是对国际竞赛规则进行全面的、深入的调研，把国际上所有的标准拿出来，包括它的强度，包括它对面料的要求，包括它对这个通风这个率的要求等等这些标准，然后我们再来对表我们的新材料，哪些是可以用的，哪些是不能用的，然后进行这个排除。同时，新材料和新结构如何整合？那我们希望通过创新，有些创新就是在规则以内开展的，有些创新是别人根本就没有定规则，而我们自己创新出一些新材料和新结构来取得优异的成绩。我想这种做法也是国际上很多体育强国所常用的。所以我们既要这个学习新规则，研究新规则，我们还要利用规则来为我们的科技助力，来搭建一个标准化、国际化的创新的这么一个机制。我回答完了。
感谢洪教授。第三个问题是说，这个无标定、无穿戴、无 mark 的3D 重建技术是全部靠高速摄像机吗？对场地的要求是什么？大概需要什么样的配置？ 室外可以用吗？
这个3D 的重建技术是我们和英特尔的团队进行了3年的合作来开展的。那么这个所有的摄像机都是基于手机的摄像头来开展的。为什么？因为我们架高速摄像机，我们架高清的摄像机，对于训练来说，这个时间上、效率上、人员上投入极大。所以我们从一开始就结合训练实践的要求，就是短平快，就是容易搭建。所以我们在场地上先做了高速摄像机和高分辨率的摄像头的这个架设，基于这些获得一些这个影像以后，进行大数据的分析、人工智能的学习，通过对这个算法的训练，不断来提高我们的捕捉精度。那么把这种捕捉精度所形成的数学模型和我们手机摄像头来进行整合。所以目前我们所提供的所有的这些数据和图像都是基于手机来开展的。目前国产手机里面高配置的一些摄像头就可以使用，这种使用既适合室内也适合室外，搭建比较容易，可以随时为运动训练提供技术数据的保障。我回答完了。
好，感谢洪校长的详细回答。我有一个小的问题啊，就是因为我们知道洪校长现在也是备战巴黎奥运会办公室常务副主任。我们这次 iCANX 大会呢，也汇集了数百位国内顶级的科研工作者。我们大批量的科研工作者都是在工程科技方面的一些专家。我想代表诸多的专家向洪校长提问。我们都希望能够去服务我们的体育科技事业，助力我们的巴黎奥运会。您对我们的科技工作者有什么样的期待和要求？
我这么想这个问题：什么是竞技体育？竞技体育所代表的奥林匹克精神是更快、更高、更强加更团结，而这种奥林匹克精神是人类突破自己的价值所在。所以，如何通过竞技体育，通过我们运动的表现，去吸引更多的人，实现自我的进步，实现自我的挑战，实现自我的升华，是竞技体育的最大价值。所以我们不断的发挥竞技体育的优势，来引导更多老百姓爱上体育，爱上健身，来把我们的健康从被动医疗转向主动健康方向。我想这是北京冬奥会有3亿人参与冰雪，应该是3.46亿人，官方统计数据。那么极大的推动了老百姓的冬天的健身热情。那么冬天里面这个白雪皑皑的大山，美好的大自然，我们的新鲜的空气，我们这个非常好的运动体验，那对我们整体的身心健康将会起到很好的作用。所以通过竞技体育使老百姓参与其中，是我们的核心价值。那么对于科学家来说，我们要关注竞技体育挑战极限的部分。到底竞技体育每一个项目，比如说田径的跑鞋，田径的服装，田径的康复装备，田径的力量训练装备，这些我们怎么样通过和训练实践结合在一起，和现场结合在一起，和教练员和运动的需求结合在一起，多听他们的声音，把我们的技术不断的和他们的需求进行对表，那能促进我们的研发。同时我们还要不断的思考这些研发怎么样向老百姓的健身需求、运动喜好来进行对接。比如这个服装，老百姓可能觉得夏天里面跑步非常热，那我们能不能研究服装来降温？那冬天里面我们在零下20度跑步又觉得特别冷，那我们如何去研发能够在低温下保暖的服装等等。所以我觉得第一个是要结合竞技体育的特点来研究专项，来切合需求。第二个是要时刻想着为老百姓服务，来解决老百姓健身中的这个刚需。我想第3个方面呢，就是要时刻注意多学科交叉。因为我在这个报告里面这张结构图所想给大家传递的目标是什么，就是让大家知道 体育不简单是体育，体育不是四肢发达头脑简单，体育是一个复杂的开放的巨系统。所以我们在研究体育的时候，我们和体育结合的时候，一定要抱着多学科交叉开放的思维来进行研究。我的回答完了，谢谢。
好，非常感谢洪校长的详细回答。我看到我们在直播平台上的观众最高数目已经达到了1.94万人，非常的火爆啊！刚才我也看到我们海霞老师已经迫不及待的想冲出来跟我们洪校长交流了，所以我接下来把时间交给我们海霞老师。
好的，谢谢啊，非常感谢冯老师。其实你刚才最后一段说的特别好，我觉得我就一个实际的例子啊，因为我本人是个体育爱好者。非常的狂热的喜欢足球，然后当然对各项体育运动都是非常非常的积极热衷，所以我说这个大家要全民参与。就您说这体育，它不仅仅是奥林匹克运动员要更快、更高、更强，而对每一个人来说都是要让自己的状态更好、更健康、更好。那同时作为科技工作者呢，我觉得从这一次来看呢，真的您讲完了，我觉得科技的这个奥运会的赛场。不仅仅是高水平运动员的赛场，也是高科技的赛道，也是国家在做这个高科技的一个很好的展示的窗口。那我前面说呢，其实这件衣服它就有一点科技和这个艺术和体育结合的这个例子，因为这件衣服是国家队的一个衣服奥运会的这个衣服是一个标签您刚才也提到了，您这个里边有很多技术呢，被我们国家一个很著名的运动员用了，他的团队服务了，提高了起跑的速度，对吧？提高了这个肌肉的训练的力量。这一个现在就是特别有名的运动员叫苏炳添。那我这件衣服上呢就有苏炳添的签名。对，我为什么会得到一件有苏炳添签名的这个呢？实际就是因为我们在他的一个合作团队里的成员就是在做柔性电子。那这个柔性电子呢，跟苏老师这个团队合作，就产生了这些非常好的一些这样前进的成果。所以我这儿呢，就是觉得特别希望跟洪老师能够就是再交流一下，就关于这个大众体育您现在这个特别多的这个技术是用在这个奥运会下一届咱们这个巴黎奥运会上，我相信有更多。那您在下一步的这个工作中，促进这个老百姓去用，就像您刚才说的研发的这些服装、这些鞋，它是会跟这些专业的运动队、运动员以他们去做这个形象代言人的形式去做呢，还是会由这些企业这些跟咱们国家这个团队来进行合作呢？就是我想了解一下，怎么样让我们老百姓能够尽快受益，拿到这些非常好的这些也有用的这样的运动鞋运动服装对，有些什么样的具体的措施在进行？
我这么去思考这个问题的，这也是我到大学以后，我也在这个新的岗位上在不断这个研究的一个方向，就是如何更好的吸引老百姓来从事体育，来进行健身。我想应该从几个方面去着手。第一个呢，是我们科技工作者要为大众人群提供更加安全、更加科学的产品，这个产品能让老百姓喜欢、爱上，并且真实的体验到它的效果。所以很多科研它有没有效，它是花里胡哨的，还是老百姓一用就喜欢，一用就上瘾，上瘾完以后还有效果，最后一看肌肉长了，脂肪降了，心情好了，对吧？每天睡得好，吃得香，这是一个方向。第二个方向，有了姚明，那么多孩子喜欢打篮球，有了李娜，网球特别火，有了林丹，羽毛球，是吧？一个场地都很难定，我们一定需要有体育明星。那我们如何去和体育明星在一起做科研？他不是形象代言人，他是科学健身的指导员，他是科学健身的宣传员，他是播种机，他把我们科学健身的知识播下去。所以如何把我们的运动员打造成健身明星，是我们科学家们、科技工作者们要共同努力，和他们这些奥运会冠军、这些明星们进行不断的这个结合的。中国人需要有阳刚之气， 中国人需要有竞技体育的这种斗争的精神。那么如何把产品和这种精神结合在一起，就像您所说的，精神和体育之美，精神和艺术之美进行结合，使老百姓真的能够欣赏体育，能够爱好体育，能够从事体育，能够享受体育。我想这是一个非常重要的课题，就是要发挥明星的作用。第三个呢，就是我们很多时候厂家去找形象代言，厂家去找噱头，那为什么不去找一些科学的噱头，找一些能够使健身效果放大的这个亮点和热点来进行宣传和推广呢？所以我们作为科技工作者，一定要和企业进行有效的对接，把企业的目标、企业的这个价值观和企业的现有的这个技术了解清楚，然后和市场的需求和技术的发展进行有机的整合，来提出热点、亮点和引爆点，使市场和老百姓健身和竞技体育三者能够形成一个良性的循环啊！我是这么看这个问题的，谢谢。
特别好。其实我觉得可能就是在您刚才说的那些运动员起到的非常重要作用里边，我觉得可能现在像这个苏炳添其实还在起另外的一个作用，就是他亲身投入到了高科技的研发当中，来进一步提升这个运动的这样一个状态。我觉得可能将来我们也有很多的运动员都可以亲自参与到这些新的装备啊、新的这样的这个研发之中，来进一步来提升，那这个效果就更好了。我相信这一定是一个就是中国体育精神的这样的又一次这样的一个腾飞和飞跃啊，不仅仅是跑得快，更重要的是知道怎么让自己跑更快，对吧？知道怎么样通过这样的一个训练，让更多的人都能跑得快，都能更健康。我觉得这就特别的给力啊！
所以这也是为什么我能接受张老师的邀请来参加本次这个学术论坛的核心，因为我平常不出席这样的这个科技报告活动，因为我很多工作这个可能不太合适去公开。但是呢，我想这样的平台，因为我知道张老师这次这个活动的平台是一个交叉学科的高端的这个有影响力的平台，所以我也在这个平台上想借机发出呼吁，更多的科学家、更多的领域、更多的专业能够和我们的体育来合作，使我们产生融合发展。所以我在此向大家表示欢迎，并且发出邀请，我们一起为巴黎奥运会中国代表团能够取得更好的成绩一起奋斗。所以衷心的希望大家能和我一起合作，谢谢。
好，谢谢冯老师。我相信科技助力这个体育以后更高、更快、更强，不仅是在奥运赛场上，在整个高科技的赛场上，在国家实力的这个赛场上，我们都会跑出更精彩的一棒。好，谢谢冯老师，今天非常感谢啊，也希望以后经常有机会大家一起来交流。那非常高兴，今天我们的这个第一场的这个大会报告结束。明天呢是我们的会议的第3天，我们上午呢还是有这个4场的这个分会的学术论坛，这其中呢就包括了刚才提到的跟体育相关的这样的一些这个论坛，就会在明天呢这个登场。然后明天晚上呢是更热闹，因为我们从6点钟就开始，一直到10点有2位诺贝尔奖获得者上来做这个演讲，也有2位全球最顶级的科学家来做这样的演讲。所以明天晚上从6点到10点，我们是一个饕餮学术盛宴，欢迎大家继续关注。后天是我们的这个 iCANX 科学大会的最后一天，白天一样，我们上午下午各有4个这样分论坛，大家来做报告。那后天的晚上我们有颁奖典礼，这一次会议上获得优秀学生论文、优秀大会论文的，我们还有另外2个重磅的这个大会报告，一个是我们复旦大学的丁建栋老师，另外一位就是享誉全球的著名的华裔科学家陈刚教授。那我也希望大家继续关注我们 iCANX， 在 iCANX 科学大会一起共享科技盛典。好，明天见。